Alright, here we go with 5-1 part 2. So if you'll remember, in the last video we talked about how do we know if a function is linear from its graph and from a list of ordered pairs. And in this video we're going to talk about how do we know if it's linear from its equation. And to start out with, the answer to that question is the equation can be written in standard form. And standard form is ax plus by equals c. And a, b, and c in that equation are numbers. Alright, we just use a, b, and c to kind of represent a number. I know that sounds weird, but that's the way we do it. So if we can write an equation in standard form, then it's linear. Well, how do we know if it can be in standard form? Well, we have kind of a list of qualifications or requirements, I guess would be a better word, that if we check these three things, then we'll know whether or not it can be written in standard form. So you want to make sure that you have these three bullets written down, because you'll be looking back at them quite often. So the first one is that x and y both have exponents of 1. And if you'll remember, we don't usually write exponents of 1. So essentially we don't want them to have exponents written at all. So if you see an x squared or a y squared or anything like that, right away you know it's not linear. Second, x and y cannot be multiplied together. So nowhere in the equation should you see x times y, or they might just write it xy. If that's anywhere in the equation, then you know it's not linear. And then finally, x and y can't be in denominators. Remember, that means the bottom of a fraction, so you couldn't have something like 2 over x. They can't be exponents, so that would be something like 2 to the x power. And they can't be underneath a radical sign. Remember, a radical sign is just a square root sign. So if you see them in the denominator, exponents, or radical signs, you know it's not linear. Now this table below just gives a few examples here. Let's start with the linear side. Here, this first one is pretty straightforward because it's already in standard form, so then I know that it can be written in standard form. If I look at the second one, okay, I could write it in standard form as you see here in the blue. I could, without even having to change it to standard form though, I can kind of see the answer. Do x and y have exponents of 1? Yes. Are x and y multiplied together? No. Are x and y in denominators, exponents, or radical signs? No. So therefore it is linear. Same thing here. I can write it in standard form as you see in the blue. But without even doing that, again, I can ask the same questions. Do x and y have exponents of 1? Yes. Are x and y multiplied together? No. Do x and y appear in denominators, exponents, or radical signs? No. So therefore it's linear. Now if we look over here at the right side, first one, you see here we have x times y. So we know right away, not linear because x and y are multiplied. Then we see an x cubed. Right away, not linear because x has an exponent that's not 1. Third one, x plus 6 over y. Right away we know not linear, y is in the denominator. So what we're going to be doing today is looking at equations and first of all determining, are they linear? If they aren't, then we're going to say they're not, and we're going to explain why. And if they are, we're going to graph them. And this will be good to give us some extra practice on graphing. So here's what it looks like. Tell whether the function is linear. If so, graph the function. So I'm going to look here at my equation and ask the questions. Do x and y have exponents other than 1? No. Are x and y multiplied together? No. Are x and y in denominators, exponents, or radical signs? No. So this one is linear. It passed all the tests. Okay, since it's linear, then I'm going to graph it. And we're going to graph it using the same method that we learned earlier in chapter 4, where we create ourselves a table I know you guys all just loved this method, but don't worry, we will learn newer methods soon. Let me just, that's not the right button I want. Alright, so linear, and I was making us a table. So I put x here, -2, -1, 0, 1, and 2. And then I had y equals 5x minus 9. I'm going to put my ordered pairs over here. So again, I'm going to plug these in. So 5 times -2 minus 9 would be -19. 5 times -1 minus 9 would be -14. 5 times 0 minus 9 would be -9. 5 times 1 minus 9 would be -4. And 5 times 2 minus 9 would be 1. So then my ordered pairs would be -2, -19, -1, -14, 0, -9, 1, -4, and 2, 1. And then what I'd do is I'd go back up here and graph these, and I'm going to count by 2's on the y-axis because they're so big. So -19 would be about right here, -14 would be right here, -9 would be like right, nope, that's -11. So like right here, -4 and 1. And then I draw a line through there, and I have okay, so let's look at the next one. Y equals 2 to the x. Now right away I hope that you're thinking not linear. Why is it not linear? Because x is an exponent, and that can't happen. Now you'll probably like the not linear ones because you don't have to graph them. Alright, so I would just write not linear, and then I'd move on. Now let's look at, last but not least, a story problem. So again, like we've talked about before, with story problems you have to consider what is a reasonable domain and range. So here we have the relationship between human years and dog years is given by the function y equals 7x, where x is the number of human years. Graph this function and give its domain and range. So x is human years, so I'm going to put that on the x-axis, and y is dog years. Alright, so let's just start 1, 2, 3, 4, 5. And over here, well, let's make our table first. And I told you before, you just have to choose 4 values. You could really choose any 4 values, except for ones that don't make sense. Now here, I hope you would know that negative values, don't make sense because we're talking about human years and you can't be -2 years old. So I just chose some low positive values. So 7 times 1 is 7. 7 times 2 is 14. 7 times 3 is 21. And 7 times 4 is 28. So my ordered pairs would be 1, 7, 2, 14, 3, 21, and 4, 28. So over here I'm going to count by sevens, just to make my life a little easier. And then I'm going to plot my points. So 1, 7, 2, 14, 3, 21, 4, 28, etc. Alright, so then if I draw my line in there, okay, and there's my graph. Notice again that I labeled. Don't forget to do that on the story problems. And the last thing I have to do is give a reasonable domain and range. Now, it makes sense that human years would go up by ones, and that they would just keep going. And we'd show that by a dot, 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 meaning it's just going to continue to go up by ones all the way down. Now the range would be the dog years. Now those, if I plug them into my equation, 1 year is 7, 2 years is 14, 3 years is 21, 4 years is 28, and then again, dot, dot, dot. That shows that it keeps going up by 7 as the domain values go up. So that's what my domain and range would look like for this particular story problem. Okay? As always, if you want further examples, let me know tomorrow. I have some more I could give you, and I will see you then.